Hello everyone, I am Engineer Ranadip Chakraborty and you are watching Bastukar the Bong Engineer YouTube channel. In the last video, I have discussed regarding how to calculate the loads coming on a column, and I have also shown detailed calculation about it. Today in this video, in continuation to the last video, what I will show you, I will show the design procedure of the column which is made of RCC. To be specific, I will be showing short axially loaded column design in limit state method. Hello everyone, I am Engineer Ranadip Chakraborty, a chartered engineer in India and a government officer, and by passion I love to educate people about civil engineering. There are a few things which are to be remembered, like minimum lateral dimension. It shall be preferably be 300 mm. Minimum grade of concrete, it shall be M20. Minimum diameter of the longitudinal reinforcement 12 mm. Minimum numbers of bars in square and rectangular column, that is 4 numbers. Maximum peripheral spacing between the bars 300 mm. Minimum and maximum percentage of steel as longitudinal steel to be used in column section is 0.8%, that is the minimum percentage, and 6% the maximum percentage. Preferably it shall not be more than 4%. So these are the basic some parameters which we need to remember for designing a RCC short axially loaded column. Now let us talk about the design steps. Step 1, calculating the influence area of the column, which we have already dealt with. If you haven't watched that video, please look into it. I am giving the link in the description box below. Go to that video and look after it, then come back to this video. Step 2, calculating the loads on the column. It is also already discussed in that video. Step 3, fixing the initial optimum steel percentage and finding the gross cross-sectional area of the column required. Step 4, fixing the lateral dimensions of the column. Step 5, checking for short column criteria. Step 6, checking for eccentricity criteria or eccentricity criteria. Step 7, finding the area of the longitudinal reinforcement and arranging the longitudinal bars. Not only we have to find the reinforcement area required or the diameter of the bars, but we have to arrange it properly, right? Step 8, finding the diameter of the lateral ties. Step 9, finding the spacing or pitch of the lateral ties. And step 10, which is the most vital part, after all this designing, we have to detail the column section so that it can be used by another person in a very easy way by just reading the drawing or the detailing of that section of the RCC design, what we are going to do, right? So these are the 10 steps for designing a short axially loaded RCC column. Some nomenclatures which we will be using during this design procedure that we must know. P is the load on the column, PU is the ultimate limiting load on the column, AG gross cross sectional area of the column, AC area of the concrete in column cross section, ASC area of the steel in column cross section, FCK characteristics compressive strength of concrete in MPa, FY permissible yield strength of steel in MPa, and L, which is clear length of column between floor and beams of it. LEF, that is L effective, that is the effective length of the column. B or D, lateral dimension of column. So let us solve a practical problem, right? First, we must get a problem to solve it. So we have a statement of problem over here. It is stating that design a square or a rectangular RCC column which is supposed to carry load of 1500 kilonewton in LSM, that is limit state method. Given floor to beam soffit height 3 meter, grade of concrete is M20 and grade of steel is Fe 500. Let's crack it, right? Step 1, calculating the influence area of the column. It is not required as load is already given and we don't need to calculate the load, right? I have already mentioned that to know how to calculate the influence area and all about influence area, the loads coming into the column, you must check the earlier video of this series, for which link I have already given in the description box, right. Step 2, calculating the loads on the column. It is also not required because it is already mentioned how the load is to be calculated in my earlier video, and in this particular case we have the load already which the column is supposed to carry, that is 1500 kilonewton. Types of main gravity loads on columns: dead loads, weight of the beam rib, weight of the floor slab, weight of the brickwork on beam, weight of the floor finishing, weight of the column stem, and live load as per IS 875 part 2, right. Step 3, fixing the initial optimal steel percentage and finding the gross cross sectional area of the column required, right. First of all, PU, that is the ultimate load carrying capacity of the column. It is 1.5 times of the load, that is the service load. So it will be 1.5 multiplied by 1500 in this case, and it is coming to 2250 kilonewton. Or if we convert in Newton, we have to multiply it with 1000, because 1 kilonewton means 1000 Newton. So it comes to 2250 multiplied by 10 to the power 3 Newton. Formula for ultimate load carrying capacity of actually loaded RCC short column as per IS 456. It is mentioned as 45, it is a mistake, it will be IS 456 2000 is PU equals to 0.40 FCK multiplied by AC plus 0.67 FY AC. Here we have PU equals to 2250 multiplied by 10 to the power 3 Newton, FCK equals to 20 MPa and FY equals to 500 MPa, right. Here we do not know what will be the AC and AC, and we need to find a way out for this, right. We know column section is composed of two materials, concrete and steel, okay. So if we take a column, RCC column, definitely it is having concrete and longitudinal steel or the main reinforcement also. So the total cross sectional area of the column, that is the gross cross sectional area of the column, is actually composed of two types of different areas of two materials, area of concrete and area of steel. So we can write that AG, that is the gross cross sectional area, equals to AC plus ASC, that is area of concrete plus area of steel. So the area of concrete is the total area of the cross sectional area of the column minus the area of the steel. We can write it as AC, that is area of concrete, equals to AG, gross cross sectional area, minus ASC, that is area of steel. That is a variable number 1 or equation number 1, and that for the area of steel we can do like AG minus AC, right. This is another variable, variable 2. Now the thing is that we can only work with one variable to solve this situation, okay. As code restricts the minimum and maximum percentage of steel, and also as it is most costly material, hence we will fix the steel area ASC on assumption and work with variable 1 only, because we already know the maximum and minimum limit of the longitudinal steel as per IS 456 2000, and also as it is a much more costlier material. So we will, from our technical experience and knowledge, will restrict the percentage of steel and then calculate upon the variable 1. So putting the variable 1 in the main formula, we get PU equals to 0.40 multiplied by FCK multiplied by AC plus 0.67 FY multiplied by AC. Now the value of the AC, which is the area, gross area of the concrete section of column minus the area of the steel, simply we are putting the value of AC in terms of variable 1, right. So PU equals to 0.40 FCK multiplied by AG minus AC plus 0.67 FY ASC. Now we need to assume some percentage of the steel in terms of AG and completely omit the term AC from the formula. So what we will do, that we will assume some percentage of steel Percentage on what? Percentage on the total cross sectional area of the column. So we can assume like 1%, 2%, 2.5%. It will depend upon case to case depending how much load is coming. If we increase the area of the steel, then we will have a slender column because area of concrete will be lesser, because steel will be take much more load, as the load taking capability in direct compression for steel is much higher as compared to concrete, and that's why if we use much higher percentage of steel, then the total size of the column will be reduced, and if we use lesser percentage of steel, then the size of the column will increase. So we have to choose some optimum value, which I am coming later on. For this case, assuming say 2.5% steel of gross cross sectional area, so ASC equals to 0.025 Ag. Simple, 2.5 by 100, I am just taking the percentage of steel in decimal, right? 2.5 divided by 100, that comes to 0.025, and multiplied by Ag, because we are taking as percentage of Ag, total gross cross sectional area. And now putting this into the formula, we get that Pu equals to 0.40 multiplied by FCK multiplied by Ag minus ASC. Now ASC comes to 0.025 Ag plus 0.67 Fy multiplied by ASC. Again we put 0.025 Ag in terms of Ag, the steel area what we have taken in place of the ASC. So if we calculate, it will come like 0.40 FCK, 0.975 Ag plus 0.67 Fy multiplied by 0.025 Ag. Now how much reinforcement percentage steel we should consider? From my experience, I have found that following percentage are suitable. If the load on the column is less than 250 kilonewton, then 0.8% steel is quite good. If the load is between 250 to 500 kilonewton, then 1% steel is quite good and holds good for that. It will produce some optimum section where you will be using almost right amount of steel, so that this section doesn't become so much bulk, and also at the same time it doesn't use so much of steel to increase the cost as a whole. And it will go on as per the chart, and finally with increase of 500 kilonewton, steel may be increased by 0.50% above this chart. These are my advice. You may also use your own values. So putting all the values we initially got in the given data into the formula we modified, we get something like this. And if we just calculate, it will come as Pu equals to 16.175 Ag. So the total load Pu equals to 16.175 Ag, area of gross cross sectional area. So we know the value of the Pu, and we can just put it into the equation and we can calculate the Ag. There is the gross cross sectional area required. It is coming about 139104 mm square. Now we can do two things. We have to now fix the lateral dimension of the column. Either we can do is that we can make a square column just by square rooting the area required, that is root over Ag, and it is coming to 373 mm to be precise. So we can take it as 400 mm by 400 mm, because we cannot take something which is much lesser than 373 mm square, and we have to make it then with next higher value. 400 mm by 400 mm is a next higher value. We can also take 375 by 375 also. The idea is that we have to make the design in such a way so that it is practicable in field, right? Like if we make 380 by 380, it is not quite practicable in many areas, because most of the masons are not habituated using the millimeter measurements. They are much more habituated in inches, feet inches. So if we can take the values in next higher multiple of 25 mm, it will be much better, as roughly 1 inches equals to 25 millimeter. Okay. Now, if we want to say produce a square section, then it is alright, we can just simply square root it, but if we want to produce a rectangular section, then we have to fix one dimension and calculate the other dimension. Considering one dimension as 300 mm, we can simply divide the value of the gross cross sectional area, as it is a area. If we can divide that area with one fixed dimension, one lateral dimension, then definitely we are going to get the other dimension. Now, if we are fixing one side as 300 mm, we will be getting other side as 464 mm. So, we can put practically a column of 300 mm by 500 mm also. What I have already mentioned, that try always to fix the column dimension in multiple of 50 mm. It is much more practicable, much more easier to do the actual work in field, right. Our design should be in such a way so that it is also easy to execute in field, because if your designs can't be executed in field, then it is simply useless. Step 5, checking for short column criteria. Now, what we have done is that we have used the formula of short column for actually loaded short column. So, we have to now check that if the column is short or not, because if it is not a short column, then we actually can't use that formula which we have already used. Okay. The criteria of a column structurally being short is that the ratio of the effective length of the column to the least lateral dimension is less than 12, right. For column with both end fixed condition, recommended effective length will be L effective equals to 0.65 times of the length, right. So, it is coming as 0.65 multiplied by 3000 equals to 1950 mm. So, least lateral dimension of the column is 400 mm, considering a square column here. Suppose we have decided to erect a square column 400 mm by 400 mm. So, least lateral dimension is 400 mm, right. Therefore, it is coming as the ratio between the effective length divided by least lateral dimension is coming as 1950 divided by 400, that is 4.875, that is less than 12. So, it is a short column, and what we have already calculated using the short column formula holds good for this stage, right. Step 6, we have to check the eccentricity criteria, right. Calculated eccentricity equals to L effective divided by 500 plus B by 30, okay, in one side, and for the other side it will be D by 30. It depends upon which side you are considering. So, it is coming as 17 mm subject to minimum value of 20 mm as per IS 456. Hence, we have to take the 20 mm value. Permissible eccentricity as per IS 456 is 0.05 B equals to 0.05 multiplied by 400 is 20 mm. So, these both are equal, or at least the calculated eccentricity is not higher than the value of the permissible eccentricity. So, we can continue our design with this thing, or else we have to check for the effects of eccentricity, okay, which will induce moment, right. Or also we can what we can do, that we can enlarge the section so that the calculated eccentricity lies well below the permissible eccentricity. Step 7, finding the area of the longitudinal reinforcement and arranging the longitudinal bars. So, what will be the reinforcement in our column? Area of steel to be provided based on the actual cross sectional area required as determined, and not upon the whatever AG provided. This is very much important. There is a tendency between engineers that whatever AG we have finally provided, like we have increased the section from 373 mm by 373 mm, which was the required section, okay. We have increased from there to 400 mm by 400 mm. So, what we have provided is much higher than what is required, right. But when we have to calculate this steel area, we have to calculate it upon the exact gross cross sectional area which is required, not what we have provided. This thing we have to remember. We have provided AG equals to 400 mm by 400 mm, okay. So, the area is coming as 160,000 mm square. However, calculation of steel area shall be based on the actual area originally required, that is upon 139104 mm square. Therefore, area of the longitudinal steel required is 2.5% of the AG, what we have taken already assumed initially, that is 0.025 multiplied by this area, it coming to 3478 mm square. So, we have to provide 3478 mm square of reinforcement, right. Now, we have done with the finding the area of the longitudinal reinforcement. Now, we have to arrange it, right. Now, we have to provide this 3478 mm square of steel in such a way that it does not exceed the maximum spacing, that is 300 mm peripherally, and also maintains the symmetry of the distribution of the bars peripherally, because if we do not provide symmetrically, then we have to make sure that it is in the direction of the greater bending. Okay. So, it is a much more wiser thing to distribute the bars peripherally in symmetry. As the column section is square, our section is already symmetrical, right, 400 mm by 400 mm. So, it is a good practice to provide symmetrically these bars. As the column section is square, 400 mm by 400 mm means considering minimum 4 bars for the 4 corners and 2 bars in between on each face, hence total 12 numbers of bars. So, there will be 4 bars at the corners, and on the each face of the column there will be 2 more bars. Okay. So, 2 times the 4 is 8 and 4 bars at the corner, 8 plus 4 is 12. So, area of the each bar required is, we are providing 12 bars. So, we will try to provide in equal diameter. So, simply what we will do, we will find out the diameter of the each bar by dividing the area required by number of the bars, that is 3478 by 12, that is 290 mm square. Hence, provide 12 numbers of 20 mm dia bars. Total area of the steel provided is 12 multiplied by 314, 3768 mm square. Okay. So, we were to give 3478, instead we are giving a little bit higher 3768 mm square, which is perfectly fine. Step 8, finding the diameter of the lateral ties. The diameter of the lateral ties are taken as the maximum of the following: 6 mm or 1/4 of the largest dia longitudinal bar. In our case, 1/4 of 20 mm is 5 mm, that is the largest dia longitudinal bar is 20 mm in our case, because we are only using one single diameter bar. Suppose we are using 16 and 20 mm, then we have to take the 20 mm value for finding out criteria 1/4 of the largest dia bar. Therefore, we can provide lateral ties of 6 mm minimum, because 1/4 of the largest dia bar is coming as 5 mm, and the criteria number 1, which is 6 mm, is maximum in between these two, 1 and 2. Okay. So, we have to provide 6 mm dia minimum. However, from all practical and seismic consideration, 8 mm dia lateral ties shall be provided, right. Step 9, finding the spacing or pitch of the lateral ties. The spacing or pitch of the lateral ties shall not exceed the following. So, it should be taken as the minimum of the next 4 criterias. One, least lateral dimension in our case is 400 mm. There is the least lateral dimension of the, if we are suppose we had to take the rectangular section of 300 mm by 500 mm, then we would have taken the 300 mm as the minimum lateral dimension or the least lateral dimension, but we have taken the square column of 400 mm by 400 mm. So, the least lateral dimension is the lateral dimension we are having, because both the dimensions are same. Secondly, 16 times the diameter of the smallest dia longitudinal bar. In our case, it is 16 multiplied by 20, as we are using the same dia longitudinal bar. So, we do not have choice, but if we used 16 mm and 20 mm, then in this case we have to take 16 mm for this criteria number 2, the smaller dia bar. Okay. Because we want the pitch or the spacing to be minimum. Okay. So, when it will be minimum, if we multiply it with smaller dia bar instead of larger dia bar, right. And in the diameter of the lateral ties, the criteria was to find out the maximum diameter, right. So, it is obvious that we have to find out by dividing the maximum dia bar, right. That is how the concept lies in. Third point is 300 mm, and fourth one is, some author also suggests 48 times the dia of lateral ties. In our case, 48 multiplied by 8, it is 384 mm. Therefore, we can provide lateral ties at 300 mm maximum pitch. However, from all practical and seismic consideration, 8 mm dia lateral ties may not be pitched more than 150 mm center to center. So, final design value what is coming up is that column section is 400 mm by 400 mm, or 300 mm by 500 mm. If rectangular sections were provided, then the requirement of and distribution of these longitudinal bars would have changed also. Longitudinal reinforcement is 12 numbers 20 mm dia bars, and lateral ties are 8 mm dia at the rate of 150 mm center to center. And the final thing is that, and it is very important, step 10, detailing of the column section. Just see how I have detailed it. I have already mentioned column cross section 400 mm by 400 mm and shown the longitudinal bars 12 numbers 20 mm dia bars, and also shown the lateral ties 8 mm dia 150 center to center. You may please check the pattern of lateral ties what I have provided. It is the correct pattern to ensure that all the bars which are there longitudinally are well secured in their place and they do not bulge out. This was the content for today's video. I hope you have liked it, and if you have liked it, then please do share my video with all your colleagues, friends and engineers, and subscribe this channel, leave your comments and your suggestion also.